Okay, better. Well, hi everyone. It's a pleasure to be here and share with you some of the results of my science work in the past few years. And apologize for, sorry for the delay with the technical issues. So my research interests are mostly about dust. Dust exists everywhere. We see it in the protoplanetary disks, in the birth cloud of stars, around the AGN, in the diffuse ISM of galaxies, which means that whether you are a theorist or an observational astronomer, whether you're interested in the physics of the ISM and star formation, or you want to design galaxy surveys to understand the evolution of galaxies throughout cosmic time, you need to take into account the effects of dust because it introduces major challenges for precision cosmology and galaxy evolution. This little tiny constituent that in terms of matter, baryonic matter in the universe, it only constitutes 1 to 10 parts per million of the baryonic matter in our universe. But in terms of energetics, dust has major roles in defining the spectral energy distribution of our universe. If you look at the SED or spectral energy distribution of the universe, obviously cosmic microwave background dominates the energy. But from the electromagnetic content of our universe that comes from galaxy formation and evolution processes, half of it is dust reprocessed light, which is called cosmic infrared background. Dust also has key roles in the physics and chemistry of the ISM. It has major important roles in the cooling and heating of the ISM. It's a catalyst for formation of certain molecules like H2. It has roles in the dynamics, in the coupling the magnetic field to the gas, and the list goes on and on. And it also significantly shapes our view of the universe by absorbing the UV and optical light and re-emitting it at longer infrared wavelengths, which means that if you look at galaxies, these are a few examples of nearby galaxies before and after James Webb. By looking at them in the infrared light, which is the dust emission, we will see a completely different view of galaxies. Regions, very highly star-forming regions in galaxies are completely hidden if we look at them in the optical light, and they will show themselves in the infrared light. And now, thanks to the advancements in the field in the past couple of decades or so, we know that dust also exists out to very high redshifts. These are some of the results from ALMA that detect dust emission at very high redshifts, redshift above 6 and 7. And now with JWST, we also are seeing significant imprints of dust in the spectra of high redshift galaxies in absorption. So we know that dust exists everywhere. And we know that it has important roles in galaxy evolution and star formation in galaxies, but how can we better study it observationally? As an extragalactic astronomer, however you want to study galaxies around us, you would need some of these parameters that are listed here. You might be interested in the star formation rate of galaxies, in the stellar mass of galaxies, or properties of gas in the interstellar medium. To understand these properties, we look at spectral energy distribution, or SED, of a galaxy, which is light on the y-axis as a function of wavelengths for galaxies. So in the next few slides, I'm going to walk you through a very simple model of an SED of a typical galaxy, different components of it. So we have the emission from stars in the UV and optical. Young stars typically emit mostly in the rest frame UV of the galaxies, and then older stars dominate the emission in the optical to the near infrared. Then we have the gas, which has strong emission lines all across the spectrum, and also a continuum emission that we can see, for example, hydrogen Balmer lines here, but it goes all the way to millimeter wavelengths. And in this picture, we also have dust that attenuates and scatters the UV and optical light and re-emitted it at longer infrared wavelengths. Depending on the distribution of dust, the properties of dust, the shape of the infrared emission changes. So to be able to model the SED of a galaxy correctly and to infer the properties that you're interested in, we need to take into account the effect of dust. Either it's in the attenuation in the UV and optical or emission in the infrared. For example, if you're a theorist, you're building galaxies, you are, for example, building dark matter simulations, you're looking at stellar to halo mass function, you would need to have accurate stellar mass measurements for galaxies. Or you're an extragalactic astronomer, you're designing large galaxy surveys to look at the evolution of galaxies. One of the important quantities that you will be interested in is the star formation rate. So as an example, both of these quantities, if we do not take into account the effect of dust, they can be underestimated for typical galaxies by a factor of 10 in star formation and a factor of 3 in stellar masses. So that shows the importance of this, taking into account dust. And as an example, as I mentioned, star formation rate, to get a total representative star formation rate of a galaxy, you need to combine the unobscured tracers of star formation, such as optical lines or the UV continuum, with the obscured star formation rate indicators in the infrared. And to put this into context of the cosmic star formation activity, this is the famous cosmic star formation rate density evolution of the universe. We know that galaxies, the content, the star formation activity content of the universe reached to a peak around redshift of 2. You can also see the look back time on the top panel, and then decline to our current universe. But interestingly, if we separate this diagram into the obscured and unobscured star formation, you see that at least up to redshift of 4, where we have direct dust measurements, dust emission measurements, the star formation activity of the universe is dominated by dust obscured phase. And at each of these epochs, if we look at them closely, look at the star formation rate of galaxies as a function of stellar mass, we see that the majority of star formation for typical galaxies is in the obscured phase. So here I'm showing a total star formation rate of these galaxies this is average in bins of mass. They are shown with star, and you can see by the percentages that more than half of them is obscured. And this is the picture we had before JWST. We needed to look at averages to see the trend. But now with JWST, we can also look at individual galaxies and understand what fraction of star formation in them is obscured. And I will talk about this plot more towards the end of the talk. So there has been also theoretical advances, models that either include dust and model the dust within the simulation, or as a post-processing add-on, they calculate the amount of dust in galaxies. But most of these models and theoretical models are unconstrained by observations at high redshifts. Here I'm showing a few examples of, for example, dust formation destruction models within a galaxy throughout the lifetime of a galaxy, all the way to looking at the attenuation properties or dust to gas mass ratio of galaxies. And with observations, we are just starting to catch up to put constraint for the models. And here, a few examples at used to be high redshift cosmic noon, but now it's maybe intermediate redshifts. From my work and my colleagues looking at the dust attenuation properties, again, dust to gas mass ratio, dust formation scenarios, and also at much higher redshifts, there has been some advances in the field. But the challenge is that we need multi-wave-like observations to connect the dust component of galaxies to the ISM, to the gas, and the stellar activity in the universe. This is, as I showed you in the SED of galaxies, this is a multi-component problem, and we need multi-wave-like observations, and that can be expensive. So my research mostly focuses on an era in the universe that is called cosmic noon, redshift 1 to 3. This is an important era to study chemical evolution and star formation in the universe, because this is where, when the universe reached the peak of star formation and black hole activity, and galaxies assemble most of their stellar mass during this epoch. But also, very conveniently, at this epoch, this is an epoch at which we can probe different phases of the ISM and of the SED of a galaxy with reasonable investment of time with our current observatories. As I'm showing here, from sub-millimeter facilities like ALMA to ground-based facilities like VLT, CAKE, and in the middle with Spitzer and James Webb, we can very nicely probe different parts of the SED of a galaxy. And because of this, at much higher redshifts, these kind of observations will be very expensive and sometimes completely impractical. So this is the highest redshift that we can learn about the properties of gas and dust in galaxies to incorporate it to the higher redshift galaxies to understand their evolution. So in this talk, I will be mostly focusing on some of the results on the UV to mid-infrared emission of cosmic noon galaxies. In the UV and optical, we look at the attenuation properties and then the reprocessed light in the mid-infrared. I will also have some jumps to the much higher redshift or much lower redshifts, just to give you an idea of what James Webb is now bringing to us. So starting with the attenuation, the attenuation curve of a galaxy shows the amount of dust attenuation as a function of wavelength, which for a very simple geometry of a foreground screen of dust in front of the stars, it will determine the shape of the observed spectrum of a galaxy. So in order to convert our observed light and observed spectrum to the intrinsic emission from galaxies, we need to know the shape of the attenuation curve. But the difficulty is that there are large variations in the shape of the attenuation curves that we commonly use at high redshift. And we don't know exactly for what type of galaxies at high redshift, which attenuation curve should be used. Most of these variations are in the slope at the UV part of the spectrum. And also there is UV features like this UV extinction bump that show itself very strongly in some attenuation curves and is completely missed in the other ones. And the even more significant importance of these variations is that it will affect our UV observations, which at very high redshifts is often the only part of the spectrum that we have. So that's why the attenuation, correcting for the attenuation is the major significant uncertainty in high redshift observations. And these variations can be due to either the geometry of dust with respect to stars. So for example, if you have a shell of dust around your stars, or a homogeneous distribution of dust with the stars, or a clumpy dust star morphology, you would get very different shapes of the attenuation curve. But it can also be due to different properties of dust grains themselves. So if you have a larger fraction of small dust grains, you tend to have a much steeper attenuation curve in the UV. Or silicate versus carbonaceous dust grains have different imprints in the shape of the attenuation curve. And of course, these two are completely degenerate, which makes this problem very difficult. If you want to determine the shape of the attenuation curve, you have both of these in the galaxies. But at the same time, it's very challenging, but also it's very rewarding if you can, for example, control for the geometry effects. You would learn by looking at the attenuation curve of the galaxies, you would learn something about the properties of dust grains in the high redshift galaxies. So that was the idea of work we did a couple of years ago. Just to remind you again, this is the census of some of the most commonly used attenuation curves in the high redshift community. So in gray, I'm showing extinction curves from SMC and Milky Way. As you can see, they're very different. At redshift 0 or close to 0, these two orange and blue curves are most commonly used. But then we see that at higher redshift, redshift 1 to 3, the attenuation curve becomes steeper, and then we see some hints of the UV attenuation bump. So in the work that I'm going to show you its result in the next slide, we decided to use a sample of galaxies with very rich data set of optical spectra and divide the sample into high metallicity and low metallicity galaxies. So metallicity is defined as the oxygen abundance in the galaxies. And then by dividing these two, we derive the attenuation curve for galaxies that have very similar distribution in their dust optical depth. So the only difference in them is the chemical abundances. And we found that indeed the shape of the attenuation curve is very different for the low metallicity and high metallicity curve. We see that the low metallicity curve has a very steep slope and no UV attenuation bump. This change in the slope is telling us something about the evolution of dust grains in low metallicity environments, such that you have a higher abundance of small dust grains, either due to shattering, more preferentially shattering in the ISM, or being less covered, shielded by the molecular clouds. So you have a higher fraction of small grains, and you get a very steep slope. Now, this change that we saw with metallicity in the attenuation curve also has important implications for another diagnostic diagram commonly used by high redshift astronomers. So the diagram is called IRX beta. It's showing the ratio of IR to UV luminosity. So it's basically dust attenuation. You have the dust absorbed emission relative to the unattenuated emission as a function of UV continuum slope. So both of these quantities correlate with the amount of attenuation. As you go to higher attenuation, both your UV continuum slope and IR over UV ratio increases. And initially, the idea of this finding the correlation between these two was due to finding a way that by only using UV information, you can correct for the dust attenuation effects. Again, because at high redshift, mostly that's the only information we have. So by calibrating UV continuum slope with IRX, you would be able to correct for dust attenuation only with the UV data. However, depending on the shape of your attenuation curve, galaxies vary in this diagram. If you have a shallow attenuation curve like the calzetic curve that I showed you in the previous slide, or you have a steeper curve, you will occupy different regions in the IRX beta diagram. And in a separate study, when we looked at the locus of galaxies at a fixed UV continuum slope as a function of metallicity, which is the color here, we find that indeed they correlate very well with metallicity, such that at a given slope, galaxies that have higher metallicity lie on the locus of the IRX beta diagram that is occupied by shallower attenuation curves. And as you go to lower metallicities, you get closer to steep attenuation curves. And this is also has been seen in the IRX beta diagram as a function of stellar mass, that lower mass galaxies tend to lie on the part of the diagram that is favored by steeper attenuation curve, which is likely due to the metallicity content. And it's a byproduct of the mass metallicity relation. Now, all of these, as you can see, is done at cosmic noon. Now with James Webb, we can extend these studies to much higher redshifts. One of the advantages with James Webb was that it's providing us with large spectroscopically confirmed sample of galaxies. Just to give you an idea, before JWST, less than 1% of known sources with redshifts greater than 6 had a spectroscopically confirmed redshifts. So this gives us a huge sample that we can now fix the redshift for them. By knowing the redshift, we can fit their SED with flexible attenuation curves and set constraints for the first time on the shape of the attenuation curve in galaxies during the reionization era. And this is some preliminary results. We are still working on it, but it shows the attenuation curve of a sample of galaxies at redshift 5 to 8. In gray, you see the shape of the curve for each individual galaxy, and the orange shows the average. And the black lines show some of the known attenuation curves. Now, to our surprise, the average curve is much shallower than the SMC curve, because we thought these are lower mass, lower metallicity, so they should have a steep curve, but that's not what we are seeing, which might be due to an actual dust grain evolution from those early times. But this is undergoing, so I won't talk much more about it, but I will go back to the UV attenuation bump that I showed you. The UV attenuation bump is a very broad feature, and it's a very mysterious feature that it was seen in the extinction curve of the Milky Way. But in different sight lines of SMC, in the extinction curve, it was completely absent. And in the LMC, for example, was something in between. At high redshifts, there has been multiple studies that some of them observed it and some of them didn't. And in this work, we saw that it's very significant at high metallicities, but not detectable at low metallicities. So we were thinking, why do we see this bump in some galaxies and not the other? What is the origin of it? And how strong it is at high redshift so that we can take it into account when we are correcting our observations for dust attenuation. And to answer those questions, we looked at the origin of the bump. PAHs, polycyclic aromatic hydrocarbons, are molecules that are suggested as the origin of the bump based on lab and theoretical work. These are large sheets of carbon-based molecules with edges of hydrogen that absorb single UV photons, get transiently heated to very high temperature, and emit in the mid-infrared in certain bands. The strongest band is at 7.7 micron, which at redshift 2 is very conveniently placed in the filter of one of the filters of Spitzer Space Telescope, MIPS 24 micron. And at the same time, for redshift 2 galaxies, using optical spectrographs on VLT, specifically MUSE, you can trace this rest frame UV spectra with very good accuracy. So we looked at a sample of redshift 2 galaxies to see if we can correlate these two features with each other so that we can pin down the origin of the bump. To look at the Spitzer data, you need to stack galaxies and look at average values because of the sensitivity limitation of Spitzers, you don't have individual detections. So we divided the sample into 4 stellar mass bins that I'm showing here with 4 different colors. First, stack the MUSE spectra. And here you see with the same colors, the stacked spectrum of each of the mass bins. The spectra is beautiful. There are just so many features. I'm showing the UV features lines with these vertical lines. But the area that we were interested in is here, the UV bump that is centered around 2175 angstrom. So we fit the bump with a Drude profile, which is the common shape assumed for the bump in these 4 mass bins. And we see that it is actually a very strong function of the stellar mass of the galaxies. So that galaxies with higher stellar mass have a very strong bump, and at lower stellar masses, it almost disappears. And at the same time, if we stack the Spitzer images, that is tracing the PAH emission in the mid-infrared, we also see a strong correlation with the stellar mass. So this was one of the main results of the paper, that if you look at the PAH strength as a function of UV bump strength, there is a very clear correlation. And these 4 are the same 4 stellar mass bins that I showed you. Now, a follow-up work of this would be to look at the metallicity of these galaxies, but that would need rest frame optical spectroscopy, and we are working on it. It's ongoing. Now, with James Webb, we can look at similar trends, but in a very much better resolution, 100 to a couple of 100 parsec resolution in the local universe at redshift 0. So this is an ongoing paper work from one of my colleagues that we're looking at FANGS data. If you're familiar with, it was one of the early science programs with JWST, that they looked at local nearby galaxies in different bands from NIRCam and MIRI. But with MIRI, in these, you can very nicely trace the PAH emission in the mid-infrared. And if you combine it with data in UV, here with SWIFT data, you can look at the correlation between the PAH strength and the UV bump. So this is the same plot that I showed you for integrated light of redshift 2 galaxies, just the axes are switched. And we again see a very clear correlation between the 2 quantities. This is a combination of regions, star-forming regions in these galaxies from 15 FANGS observations. So this was at redshift 0. We can also, with James Webb, look at it at much higher redshifts. So in a study last year, with the very first data from JWST, we saw that we saw a very strong indication of the bump in a redshift 7 galaxy. Now, this was very exciting because you wouldn't expect this large amount of dust in such young galaxies. So if you look at it in terms of dust production scenarios, this diagram shows the bump amplitude from different studies. Some of these are the study that I showed you before as a function of redshift. And this is the highest redshift galaxy that bump has been discovered in spectroscopically. The vertical line, the vertical dash line, shows the minimum carbon formation timescale for this galaxy if it's formed at redshift 10. And as you can see, it's very close to where time-wise, where we detect, where we have this galaxy. So it's challenging the scenarios of dust formation, because if you need PAHs that are commonly thought to be produced in the outflows of AGB stars, you need a few 100 million years for these stars to produce the dust grains. And the bump is just too strong to be able to easily explain it with this source. So there might be other ways of producing PAHs in these galaxies through AGB stars, AGB stars through supernovae or Wolf-Rayet stars that have much shorter timescales. Now, going back to our sweet spot of redshift 2 or cosmic noon galaxies, all the results that I showed you before was based on Spitzer data. But MIPS or Spitzer MIPS at 24 micron. But Spitzer had sensitivity limitations, particularly because of its small aperture. It was confusion limited. Here in gray, I'm showing the infrared SED of typical galaxies at redshift 2, the range of their dust SEDs. And the blue arrow shows the confusion limit of Spitzer MIPS 24 micron. As you can see, with the Spitzer, we were only able to detect the tip of the iceberg. We were missing most of the galaxies at that redshift in the universe. But now with MIRI on James Webb, with very moderate amount of integration, 10 to 20 minutes, we can get down to an order of magnitude better sensitivity, detecting most of the population at these redshifts. So this brings me to our GTO survey, SMILES, Systematic Mid-Infrared Instrument Legacy Extragalactic Survey. It's a mouthful. So SMILES is the largest continuous MIRI survey in the first 2 cycles, from 5 to 25 micron, that exists in the first 2 cycles. Here I'm showing the footprint of the survey. It's centered on one of the most studied extragalactic fields, good south. 15 pointings. Each of these squares is one of the pointings of MIRI pointings. We observed in each pointing from all the way from 5 to 25 micron in all the 8 bands. So the observations were done about a year ago. Last January, they were finished, but then took us many months to have fun with the data reduction of this new instrument and new telescope. I just wanted to do a flashback to MIRI commissioning. So since then, we were engaged with understanding MIRI. There were multiple, not issues, but things to understand, from the PSF to background, etc. And you can actually see here our own Javier, very hard at work at a space telescope. It was an amazing time. The experience of those 6 months of commissioning was probably one of the most memorable and fruitful experiences that I had during my career. But anyway, after months of dealing with the data reduction, as of a few months ago, we have our survey completely reduced, and it's beautiful. Believe me, there are more galaxies if you look at the FITS maps, but there are all sorts of colorful galaxies. This is a color image from 3 MIRI filters, and it's like jelly beans. There are like red and green and blue galaxies coming in and out. But I want to focus on 2 galaxies to just show you the power of this data set. So this is a galaxy at redshift 0.4. On the left, you see the NIRCam image of it, which has much higher resolution and sensitivity, and you can see all sorts of structures in it. What we had before MIRI is the Spitzer MIPS I'm showing on the right. It's just a huge blob. you can't really detect any of the structure. And in the next couple of images, I'm going to show you the MIRI image of these galaxies in a few different filters. You can see these different clumps of star formation are coming in and out depending on where the filter is situated. And it's the first time that we can actually resolve star-forming clumps in these galaxies beyond the local universe. And as another example, this is like an association of galaxies. I like to think of it as a redshift 2 Stefan quintet. So these galaxies are each located at a different redshift from 1 to 2. And this is what we had before with the Spitzer. Again, a huge blob. You wouldn't be even be able to separate the light of these different galaxies. And now with MIRI, we can look at them separately in different filters, and they are getting fainter or brighter depending on, I'm going to show you again, depending on which filter, where it's tracing the mid-infrared emission of these galaxies. So more quantitatively, this is an SED example of one of these galaxies at redshift 1. It has marvelous coverage from HST and NIRCam, and then MIRI tracing the mid-infrared dust emission. And one of the powers of having this full wavelength coverage is that we can very well separate the AGN emission from star-forming emission in these galaxies. So all of these are at the same redshift, but range from top to bottom, they are ranged from a star-forming dominated galaxy to an AGN dominated galaxy. And as you can see, because AGN has a hot dust component, it has a very power law shaped dust emission in the mid-infrared, which is completely different from the PAH emission that is coming from star formation. So one of the first studies with our survey, led by a postdoc, John Wei Liu at the University of Arizona, was looking at the population of AGN at cosmic noon. And these different circles show the AGN identifications using different methods. And as you can see, there was a large fraction of newly discovered AGN based on the MIRI data. Even at for the very massive galaxies that other surveys are supposed to be complete, we found about 30% new AGN detected by MIRI. Well, this is all I'm going to say about AGN. My research focuses on star-forming galaxies. So I removed all of those AGN, and I look at the star-forming galaxies, which I'm showing their population here in the star formation rate versus stellar mass diagram. So again, to just give you a sense of the data we have, I'm showing examples of SED for a starburst galaxy, so above the main sequence, for a galaxy below the main sequence, a very low mass galaxy, and a typical main sequence galaxy. So main sequence, we call it for typical galaxies at different redshifts in terms of their star formation and stellar mass. The typical ones we call the main star-forming main sequence. And one of the quantities we can very well measure with this data is the mass fraction of PAHs in the galaxies, which is coming directly from the mid-infrared constraints from MIRI. So at redshift 2, the PAH fraction, so this is the fraction of dust mass that is in PAH molecules. At redshift 0, it has been studied in many studies. So this is one of the typical reference redshift 0 studies that I'm showing here, that PAH mass fraction as a function of metallicity has a very strong correlation, such that at low metallicities, we have very low PAH fractions, but then it suddenly gets to an almost constant value at higher metallicities. We couldn't study this at higher redshifts. So with MIRI, this is the first time we are looking at it. Here again, I'm showing a compilation of redshift 0 studies. They're in different colors because the way they derive the metallicity is slightly different. So for completeness, I showed all of them. But again, if you remember, we see a high value at high metallicities, and then they drop with a large scatter. To just give you a better illustration, I'm also showing here the running median value for these two samples and a fit to the running median in the bottom panel. Now, if I add our redshift 2 galaxies, they are exactly on top of the redshift 0. And if you look at the trend, it follows very well what we had before at redshift 0, which shows that this relation, the correlation between the PAH fraction and metallicity, is not evolving with redshift. It's probably a universal relation. So what we are seeing is that at high metallicities, above half solar, we have a constant high PAH mass fraction of about 3 to 4%. Then it drops to very low values at very low metallicities, less than 1%. And in between, there is a very steep decline of this quantity. Now, the reason behind this trend is still out for debate. We don't exactly know, but there are two different scenarios. Either the PAHs are not either they are preferentially destroyed in the low metallicity environment because they are less shielded and more susceptible to hard ionizing radiation, so they can be destroyed. Or they are not produced in sufficient quantities at low metallicities because these systems are, first of all, young. So the AGB stars, for example, that are responsible might not have been evolved enough. Or that there are also theoretical models that show as the galaxy ages, you would produce more PAH grains when the metallicity evolves at later ages. Yes, so the reason is still needs more observations and different sorts of observations, but we are seeing for the first time at redshift 2 that we can quantify it to be very similar to local universe. Now I want to move on to, or actually circle back to what I mentioned at the beginning of the talk. Another interesting quantity that now we can measure with MIRI is the fraction of obscured star formation. Now, if you remember, I mentioned that one of the most significant uncertainties in measuring star formation rate of galaxies is the dust obscured fraction. Before JWST, this has been studied using averages or stacks of Spitzer data. And this is the trend you see here. On the y-axis, you see the fraction of obscured star formation rate as a function of stellar mass. And one of the findings of this study was that this trend doesn't change with redshift. So at all redshifts, at a given mass, you have a certain amount of obscuration. But the scatter in this relation is completely lost in data from Spitzer because you don't have individual detections. And now we can look at the scatter. This is from the SMILE survey. And if I want to put it into context of the previous study, the dotted curve is the curve from MIPS data before JWST, which is biased a little bit high compared to our results. And that's because in Spitzer data, you're missing most of the population that is less obscured. But with MIRI, now we have the sensitivity to look at all of them. Now, two takeaway points that are very interesting in this plot is that above stellar masses of about maybe 10 to 9.5, on average, more than half of the emission of galaxy is dust obscured. But at all masses, at least the ones that are arranged in this study, because there's a large scatter, you see heavily obscured galaxies, even down to very low stellar masses, which makes it very interesting to understand processes that is causing such large scatter in the fraction of obscured emission at a given stellar mass. So we looked at different secondary correlations to better understand it. And we found that there is a strong correlation with the size of galaxies. So at a given mass, the galaxies with lower obscured fraction are also smaller compared to their counterparts with higher obscured fractions. Now, I want to pause here again and again remind you, this is for the first time we can measure dust obscured sizes for these galaxies, which is representative of where the star formation is actually happening. Before this, all we had was shorter wavelength data, which is not showing where the actual star formation is happening. So this is another comparison between the Spitzer data with a 6 arcsecond full PSF compared to the MIRI data. So what we're seeing is that at a given stellar mass, higher obscuration in galaxies happens in galaxies that have also more compact star-forming regions. So this is for the highest mass bin in the sample. But when we divide it into different stellar masses going to lower and lower stellar masses, as expected, with increasing stellar mass, your obscured fraction also increases. This is what I showed in the previous plot as well. But at a given mass, we are seeing that the more obscured galaxies have higher star formation surface densities or more concentrated star forming regions. This has been seen in the past with ALMA data as well, but for much more massive and star-forming galaxies and much smaller samples. And we can explain it with a very simple cartoon. If you have an extended star formation region in your galaxy, the dust to stars morphology is very complex. You have some stars that are enshrouded in their very dusty birth clouds, while other stars are in the diffuse ISM and less obscured. So you will get a lower, on average, obscured fraction. But if you concentrate all of that into the central region of the galaxy, you tend to have a higher covering fraction of dust. So most of the light emitted from your stars is now completely obscured by dust. Therefore, your star formation obscured fraction increases. And now looping this back to the IRX beta diagram that I showed you earlier, we see the same trend, that the scatter in the IRX beta diagrams can also be explained by the star formation surface density of galaxies. At a given mass or UV continuum slope, galaxies that have higher IR to UV ratio have also more concentrated or higher star formation surface densities. Now, this can be because they, on average, have higher dust optical depths, or that, or at the same time, also, they have a more compact geometry and higher fraction of their stars is obscured by dust. Now, these were some of the results with the JWST. We are just at the beginning of the way, and there is a lot more to be done with this amazing telescope. But at the same time, I would also like to always keep an eye out for future facilities. And one of them that I'm very excited about is a far infrared probe in space. There are these two concepts that I worked on in the past couple of years, PRIMA and SPICE. And PRIMA was actually submitted as a concept last year to NASA, and we'll hear about it, I think, in summer. But it's a cold, single dish mirror observing in far infrared. So we will be able to extend all of these studies to much higher redshifts close to the reionization epoch. And with that, I will leave you with my summary slide.
Well, thank you very much, Irene, for that fantastic talk under very difficult circumstances as well. So I think extra kudos for that. So if anyone would like to pose a question here in the room first, and then we'll go to Zoom, and then we'll come back. Sorry.
Thank you very much for the nice talk. I'm losing my voice, so I hope I can finish my question. So if I understood correctly, you find these two populations of galaxies with low metallicity. So they show also lower pHs, so lower, and then the high metallicity, higher amount of pHs. So I was wondering the redshift range that you have used for that study, and whether you expect to find any changes in that behavior for higher redshifts.
So the redshift range was between 0.7 to 2, so it's quite a wide redshift range. And we don't see any change in the average trend with redshift between these. And it's the same as what has been observed before at redshift 0. So both the obscured fraction and the pH mass fraction as a function of metallicity trend, they seem to be redshift invariant. And if I extrapolate it, I would say it's the same at higher redshifts. Although there is a slight side note to that. So the way we measure metallicity is oxygen abundance. which is not necessarily the parameter that would derive changes in the ISM that affect PAHs. So, for example, iron abundance is a better approximation if you're looking at the intensity and hardness of the ionizing radiation. And we know that, for example, at redshift 2 compared to redshift 0, galaxies have a super oxygen to iron abundance. So if we keep the oxygen abundance as our metric, there might be a change in that sense.
Back at the back there.
Hi, Irene. Really nice talk. I think maybe I missed that, but I really like your distribution of oscillation as a function of mass of the galaxy. Have you, since you also had a lot of points there, have you made the reverse thing, the distribution of the number of galaxies, or which is your top, I mean, your most common oscillation fraction for the redshift 2 to 4 range that you observed? Is that very peaked? So if you go to your diagram where you have all these blue points, so basically
There are a lot here.
Yeah, it should be something like around here.
Yeah, I haven't, it's a good point. I haven't looked at that, but
you could just do some kind of binning and do a distribution function of the number of galaxies for a given oscillation. So basically it will give you also that will be a representative main sequence distribution of your galaxies, isn't it?
Yes, no, that's a good point. There are lots seem to be here, and I haven't done it quantitatively, but the interesting thing is that if I try to fit this data with a similar function as was done before with the Spitzer, and taking into account the uncertainty of each individual galaxy, we'll get a very similar curve, which means that in this trend, the very obscured systems that also have lower uncertainty completely dominate. But there is this huge tail of the distribution to lower obscuration at a given mass. That's, back to your point, would be interesting to actually look at, quantify it.
Yeah, and just a second point, I don't know if you guys can ask about that. Basically, is related to this metallicity as oxygen, which you expect to be more dominant because of the very massive stars at the beginning. What about carbon? Because the dust is coming from carbon, so you don't expect carbon to be correlated with oxygen.
Yeah.
So what is the trick?
Yeah, so I don't know of any study that looked at the carbon abundance with PAH. But the thing is, if the galaxy is very young and you have really low carbon abundance, then you would expect to not see PAHs. But it's very quick after that it has enough carbon that you might not see any correlation with the PAH fraction, because then you need other processes to turn that carbon to PAH. So what I'm saying is that very low carbon abundances probably we have very low PAHs, but then after that it's probably okay.
Okay, we'll go to Miriam next.
Very, very nice talk. So I have 2 questions. One is very naive. The other one is more related to the kind of work I do. The naive question is, so apparently, if I understood correctly, the amount of PAHs in a galaxy correlates positively with the star formation rate. So I suppose you would have more massive stars. So I would think very naively that with a harder and a stronger ionizing radiation, such a big molecule would be more unstable. So I was wondering if you knew something about that and if you could explain a little bit.
No, yes, definitely. Like if you have a burst of star formation, so if you have, for example, a very young system that has not young, if you have a burst of star formation, like very high specific star formation rate, you see lower PAH fractions. And I think that is because of the the PAHs, the molecules being photodissociated by the radiation. But on global scales, If you have more star formation, you produce more dust, and by scale, you will produce more pH as well. However, in the quantities that I show, for example, pH mass fraction, that should be corrected for, because that's looking at pH mass to overall dust mass. So that's why when we see a trend with, for example, mass with the pH fraction, then that's something that's telling us something about the pH production or destruction itself, not just bigger is bigger, like not just that you have more star forming or more mass, so you have more dust, because it's already normalized to the total amount of dust. Does that make sense?
And the other question is, I think I saw a plot, I think it was the IRX plot versus beta slope.
Yeah.
You were comparing with SMC values, and I thought I saw the SMC quoted as a 1.4 solar metallicity.
Oh,
So
yes, yes.
I was wondering if you could explain that, because
Yes.
in the massive star field, the SMC is the reference for metal per environment. So that was a bit shocking. And also, if you know what kind of sightlines they use for that, because obviously the SMC is resolved. And,
Yeah. No, good catch on the caption. So this is an average SMC curve, average over different sightlines, timeline. But so I'm showing both for 0.14 solar metallicity and 1.4 solar metallicity, so a factor of 10 different. And the reason is that depending on the metallicity, your intrinsic UV slope changes. And that will shift the locus of galaxies to left and right in this diagram. So I think actually in this, yeah, here. So you would have, for lower metallicity, you will have a bluer intrinsic UV slope, so it will move it. So just to be complete, I show, this has been calculated by assuming a curve like SMC or a Calzetti curve in a stellar population synthesis modeling, and then having two different metallicity assumptions, and then calculating the UV slope, intrinsic UV slope, and then also the shape of the, yeah.
Yeah, that makes sense.
Okay, so do we have any final questions in the room here, or possibly question on Zoom? Can anyone check that for me?
I don't see any.
I requested the Zoom attendees